In the wide and almost empty dark mass settles into quiet presence and space-time answers by bending slowly, almost imperceptibly at a distance. Gravity here is not a pull, but a shape, and motion honours that shape without protest. Free fall becomes the simplest form of travel, not by force but by geometry and light itself, though without rest mass still follows the curves that the geometry sets. A geodesic is the straightest path the universe permits in a curved arena, and so the straightest path is a curve, a calm compromise between direction and the form of the world. This is a first soft irony. Straightness survives by bending. Far from any compact object, the bending is slight, yet its slightness carries measurable consequence. Starlight that passes near a star does not keep the course a flat drawing would promise. It deflects by a small angle that reveals the curve. During a solar eclipse more than a century ago, astronomers measure the apparent shift of distant stars near the sun's limb by about 1 3/4 arc seconds, a narrow slide of position that confirms the prediction of general relativity. The detail is modest and real, a thin numerical seam between idea and sky, and it hints at the broader lensing that makes distant galaxies appear as arcs and rings when background and foreground align. Another soft irony waits there. The brightest rings may frame the darkest places. Curvature touches not only the map of space, but also the rhythm of time. Clocks that rest deeper in a gravitational well tick more slowly than clocks set higher up, and light that climbs outward loses energy and drifts into redder wavelengths. Gravitational redshift is not metaphor but measurement written in spectral lines that lean toward longer colors when they emerge from stronger fields. Two synchronized clocks that part ways at different altitudes later disagree with absolute certainty, each faithful to its own local rhythm. It is quiet and exact, and it introduces a third soft irony. The closer clock falls behind, while the more distant clock runs ahead, so separation in height becomes separation in time. The rulebook behind these effects is not a painted backdrop. It is the stage itself written as a metric that tells how distances and durations are counted, and as a connection that tells how directions carry themselves along a path. Free fall is the refusal to fight that stage. Nearby geodesics do not remain parallel. They converge or spread according to the Riemann curvature that quantifies how the world departs from flatness. In the language of deviation, two particles released gently side by side can drift toward one another, or apart without a single force in the ordinary sense, only the guidance of the shape they inhabit. A familiar analogy softens the picture without replacing it on a globe. A straight course is a great circle, and a traveller who never turns still curves across the surface, not by choice but because straightness and shape agree to mean something new together. Gravitational lensing grows from this same geometry. When alignment is precise, background light arranges itself into halos that nearly close, forming rings, named for the thinker who traced their logic. The glass is not glass, the lens is the field itself. A ring may be steady where the mass distribution is quiet or warped, where structure intrudes, and it tells of distances and masses with a precision as calm as the images it traces. The brightest ring can mark a center that remains unlit, a placid reminder that in curved space-time illumination obeys a map that no lamp designs. As mass becomes more compact, the sag deepens, and the options left to light narrow. For a non-rotating black hole there exists a special shell where photons can orbit a photon sphere at about 1 1/2 times the Schwarzschild radius. It is a delicate place in the geometry where a single nudge decides escape or descent, and though it sits just outside the strongest shadowed region seen in images, it remains a real property of the space-time, not an ornament. This is the quiet, lesser-known detail that foreshadows the threshold to come an orbit for light itself, balanced on a knife edge of curvature. The slow curve that governs all of this is a conversation without a voice. Matter and energy say how spacetime bends. Spacetime tells matter and light how to move. The exchange continues with no sound, only consistent outcomes. Behind this order rests a question that stays open with care. Where does the smoothness of the stage come from, at the smallest scales, and what replaces smoothness when the word loses meaning? Whether spacetime is continuous all the way down, or whether it arises from more fundamental quantum relations remains unsettled. The search for a quantum theory of gravity proceeds with patience, and its hints remain gentle rather than conclusive. Some proposals suggest that entanglement patterns may help to weave geometry, but the loom itself is not yet known. The approach toward an event horizon begins here in effects that are already present and measured far away. No sudden boundary announces itself in the outskirts, only a deepening of the same tendencies. Light bends a little more, clocks in wells lag a little further behind their distant partners, and paths that seek to remain straight must curve more obviously to keep their promise. The motifs gather like a refrain, light stretches, clocks diverge, shadows ring. The field equations themselves do not appear, yet their implications stay close to every sentence, as if a score were guiding a slow piece without showing any notes. From these first quiet truths the rest will follow. The world is a shape that tells matter and light where to go, and the journey inward is nothing more dramatic than following the shape faithfully. In the end, the last soft irony of this opening remains in view. Emptiness is not empty, for the vacuum bears a structure so exact that it times clocks, bends, beams and directs motion with a steadiness more reliable than many solid things. The pace stays even. The sky does not hurry. The curve deepens almost without remark, preparing a boundary that no signal can cross outward, while still allowing the calm passage inward that geometry permits. The threshold waits ahead, but the rules that make it are already here, written in the slow curve that turns straightness into a patient arc. The thin halo forms where light is caught between the choice to leave and the inevitability of falling inward, a luminous edge drawn not by matter, but by the curvature itself. At the photon sphere roughly 1 1/2 times, the Schwarzschild radius for a non-rotating black hole photons trace paths that close on themselves, circling without rest, yet in a balance so unstable that the smallest deviation in direction sends them outward to the universe or inward toward the horizon. This place is not a material shell, but a set of possible paths in the geometry, and it exists for any observer to calculate, though never to touch. The brightness seen in this ring is an accumulation of light from many directions, bent into the same outline, an optical echo of the spacetime's precise curve. This is the first quiet irony here. Light which moves at the fastest possible speed can still be delayed into orbit by nothing more than the structure of emptiness. From a distance, the ring seems fixed and sharp, but each photon in it is temporary, tracing perhaps a fraction of a turn before being lost one way or the other. The halo is therefore a constant renewal, its image steady, though its substance continually replaced. The second irony rests here. Something can appear unchanged only because it is in perpetual change. In observations such as those from the Event Horizon Telescope, the ring is not perfectly uniform. Magnetic turbulence in the accretion flow, irregularities in the distribution of infalling plasma, and the orientation of the black hole relative to Earth all shape the final image. The glow is brightest where matter is approaching at near light speed toward the observer, an effect of relativistic beaming that amplifies light in the forward direction. Opposite that point where matter is moving away, the brightness fades. This is a third soft irony. The most intense light we see comes from matter that is moving most swiftly toward its own disappearance. The photon sphere's existence follows directly from the form of the Schwarzschild metric. In this geometry, The effective potential for light has a maximum at that specific radius, and like a marble balanced on the crest of a hill, the orbit there is in unstable equilibrium. Any perturbation inward drops the photon toward the horizon, any perturbation outward lets it escape to infinity. For a rotating Kerr black hole, the situation changes subtly. The radius of the photon orbit depends on the direction of travel relative to the spin drawing co-rotating photons closer and pushing counter-rotating ones farther out. In extreme rotation, co-rotating photon orbits can come as close as the event horizon itself. Yet for all these variations, the essential feature remains spacetime here is bent strongly enough to fold the path of light into a closed loop. The reality of this structure is supported not only by theoretical calculation, but also by indirect measurement. Lensed images of stars or hot gas near black holes, and the detailed brightness profile of the EHT images of M87s all reveal patterns that match the predictions for light trapped near the photon sphere before escaping outward. The thinness of the ring is itself a measured detail telling of how quickly photons either fall in or fly away once they are perturbed. The physics that shapes the photon sphere also shapes the broader gravitational lensing environment around the black hole. Light from background stars can loop around the black hole multiple times before escaping, creating a sequence of ever fainter, more compressed rings inside the main halo. Each of these higher-order images carries information about the geometry extremely close to the horizon, though in practice the outermost and brightest ring dominates what telescopes can resolve. The photon sphere is not a place one could ever reach without becoming light oneself. Matter approaching it follows time-like paths, and those paths cut across the photon orbits rather than joining them. A spacecraft, if imagined to fall inward past the photon sphere, would simply cross this radius as part of its continuous descent, seeing nothing unusual in its own frame, except for the changing pattern of incoming light from the outside universe. This brings the gentle reminder that many of the structures named in relativity are not material surfaces, but geometric features defined by how light and matter move. The photon sphere's instability also plays a role in how black holes interact with their surroundings. The concentration of photon trajectories near this radius increases the intensity of radiation from the inner accretion flow, contributing to the distinctive spectral signatures in X-ray and optical observations. In particular, the broadening and skew of the iron K-alpha line observed in active galactic nuclei arise in part from photons that skim close to this orbit before climbing outward. The gravitational redshift and Doppler shifts combine into a profile that is asymmetric, with a sharp cutoff on the blue side and an extended tail on the red, a shape that encodes both the speed of the gas and the depth of the gravitational well. A lesser-known detail in this region is that gravitational time delay affects not only the path of photons, but also the arrival sequence of signals from transient events. A flare of radiation from a hotspot orbiting near the innermost stable circular orbit can be lensed so that multiple images reach the observer at different times, some of them delayed by paths that loop around the photon sphere. The delays are measurable in principle and can be used to test the predictions of strong-field general relativity. Yet even here, where theory matches observation closely, questions remain. The exact influence of plasma dispersion near the photon sphere is not fully resolved, and distinguishing gravitational effects from magnetohydrodynamic variations in the flow is an ongoing task. These are quiet mysteries approached slowly with data and modelling where certainty arrives in increments rather than in sudden revelations. The photon sphere serves as both a boundary in the behaviour of light and a marker on the way toward the event horizon. From the outside, it is the last stable orbit for light itself. From within, it is only another radius crossed in the steady fall. Between these perspectives lies a simple truth. What appears as a fixed luminous ring is only a pattern made by countless individual photons, each on its own brief path. The structure that holds them is not solid but purely geometric, a curve in space-time that can neither be seen directly nor erased, while the mass that shapes it remains. Light stretches here, but it does so in a loop. Clocks diverge, but the light in the ring does not keep time. Shadows ring, but their edge is drawn by brightness. The inward path continues, and the next threshold waits invisible from within, but certain from without. The halo fades behind, replaced by the growing influence of a horizon that still lies ahead, its presence defined not by sight, but by the future paths of every signal that approaches it. The event horizon lies ahead without shimmer, without outline, without any surface to scatter or reflect the light that approaches it. From a great distance, it presents itself only through the delay and fading of signals from anything that falls toward it. The mathematics says it is a null surface traced out by light that remains forever on the boundary between escaping and being drawn inward. For a distant observer, the descent toward this boundary appears to slow the last visible moments of the infalling object stretched over an infinite time, its light increasingly redshifted, until no wavelength remains within the band that instruments or eyes can detect. This slowing is not a hesitation in the falling object's own frame. Rather, it is the divergence of clock readings between the two locations, a direct consequence of the space-time curvature. This is the first soft irony here. What seems to pause from one vantage continues without pause from another. The gravitational redshift in this region becomes so extreme that even photons with the highest energies lose their sharpness to the distant observer, sliding into invisibility. Spectral lines that were once narrow and distinct spread into long wavelengths until their structure disappears into noise. The loss is not destruction, but a migration beyond the reach of detection, and in principle the information is still there, though in practice it is gone for any measurement. This is the second irony. The path from source to observer remains unbroken, yet the content of that path becomes inaccessible. For the one who falls, the horizon is no more dramatic than crossing an arbitrary radial coordinate. There is no sudden change in the local environment. No heat, no impact, no signal marks the crossing. The metric continues smoothly, and local physics obeys the same rules on both sides. The difference is in the causal structure beyond the horizon. Every possible future path is directed inward toward the singularity, and none can turn outward to reach the external universe. This is the third soft irony. A point can be both ordinary and utterly decisive, depending on which way time points in the geometry. In the Schwarzschild solution, the event horizon lies at a fixed radial coordinate equal to twice the gravitational radius. In the Kerr geometry of a rotating black hole, the horizon's position depends on the spin parameter, and it is accompanied by the ergosphere outside it, where space-time itself is dragged around in the direction of rotation. Yet in both cases, the horizon is not a material object. It is a global feature of space-time, the outer boundary of the region, from which escape is impossible. The horizon's existence is established through both theory and indirect observation. The absence of any detectable surface emission from the compact objects at the centers of galaxies, the patterns of light bending and shadow size measured by the Event Horizon Telescope, and the behavior of stars orbiting close to Sagittarius A, all support the conclusion that these objects possess horizons rather than hard surfaces. One lesser-known detail is that the size of the shadow in an image is not the same as the size of the horizon itself. The photon sphere lies outside the horizon, and it is this sphere that defines the diameter of the dark region in the image. For a non-rotating black hole, the shadow's apparent diameter is about 2.5 times the radius of the horizon. This means that the boundary we see is not the boundary that defines no return, but a projection of light paths that just miss capture. As an infalling object approaches the horizon, the tidal forces it experiences depend on the mass of the black hole. For stellar mass black holes, the curvature becomes strong enough to stretch and compress the object well before the horizon is reached. For supermassive black holes, the same forces can be negligible at the horizon, allowing the crossing to occur without immediate disruption. This difference illustrates the scale dependence of the geometry's gradients, and it adds a further subtle irony. The largest black holes are the gentlest at their edges. Theoretical studies of the horizon also extend into the realm of quantum field theory. In the semi-classical picture, the vacuum near the horizon is not empty, but filled with virtual particle pairs. One member of a pair can escape as Hawking radiation, while the other falls in a process that slowly reduces the mass of the black hole. For astrophysical black holes, this radiation is far too weak to observe, yet the effect is mathematically inevitable, given the combination of general relativity and quantum mechanics. The horizon thus acquires a temperature and an entropy proportional to its area, linking thermodynamics to gravity in a way that remains one of the deepest connections in theoretical physics. A quiet mystery remains here unresolved for decades. What becomes of the information about the quantum states of the matter that falls in? If Hawking radiation is purely thermal, it seems to carry no details about the interior, suggesting that information is lost. This would violate unitarity, a principle of quantum mechanics, yet no definitive resolution exists. The information paradox, as it is called, is a question that reaches to the foundations of both relativity and quantum theory, and any answer would have to reconcile their principles. Observationally, the approach to the horizon is seen not in the details of the crossing, but in the fading of signals. X-ray binaries in which matter falls onto a black hole show rapid flickering as magnetic fields and turbulence in the accretion disk shift the flow of plasma. As material approaches the innermost stable circular orbit, the frequency of this flickering can change, offering a measure of the black hole's mass and spin. Once past that orbit, the matter plunges inward and its light is quickly lost. The disappearance is smooth in theory, but sharp in practice because no telescope can follow photons that no longer arrive. The horizon's invisibility is therefore not a limitation of technology, but a feature of the geometry. There is no outgoing light from within. Light stretches here in wavelength and in time. Clocks diverge, one ticking ever slower in the view from outside, while the other marches evenly in its own frame. Shadows ring with the photon sphere's light, framing a place that can no longer send any message outward. The crossing is quiet, the boundary without texture, yet in the map of spacetime it is the most absolute division. Beyond it, the interior geometry directs all events toward a single fate, while outside orbits and light paths still have the freedom to turn away. Infall continues without pause, and the horizon recedes into the past of the traveller, even as it remains forever in the future of the outside universe. The journey goes on now entirely within a region from which return is not possible, yet still governed by the same laws, the same curvature, and the same unbroken rhythm of fall. Inside the horizon, the coordinates that once described space and time exchange their roles in a way that is not metaphor but exact geometry. The radial direction becomes as inescapable as time itself, so that moving inward is not a matter of choice or propulsion, but of following the only future that the space-time allows. Every geodesic within the horizon curves inevitably toward the singularity, and no path can lead outward. Even light, which outside could circle or escape, now finds all directions bending inward. This is the first soft irony. Motion here is no longer about direction in space, but about the inevitability of a timeline that ends at a finite proper time ahead. In the equations, this change appears as the sign of the metric components swapping across the horizon, but for any freely falling observer, the physics remains locally the same. There is no force dragging them. there is only the structure of spacetime assigning the singularity as every worldline's future endpoint. The curvature grows as the center approaches, and the way it acts on objects is described by the tidal tensor, a measure of how nearby geodesics converge or diverge. The second soft irony lies here. The same geometry that guides without resistance can stretch one part of a body, while squeezing another all without any contact or medium. For a small black hole, this tidal stretching becomes extreme well before the singularity separating molecules and atoms in a process called spaghettification. For a supermassive black hole, however, these forces may remain gentle until very close to the center, allowing an observer to pass much of the interior without feeling them directly. A lesser-known detail is that the spacetime curvature is not uniform even within the horizon. It depends on the angular momentum and mass of the black hole, and in rotating solutions the inner geometry contains regions where tidal forces can briefly reverse direction before increasing again. Infall within a Kerr black hole also encounters the frame-dragging effects that began in the ergosphere outside. Inside, this dragging becomes absolute spacetime itself, carries everything around in the direction of rotation. The concept of standing still relative to distant stars loses all meaning. This leads to the third soft irony. The fastest rotation one could imagine. Achieving here is not motion at all, but simply being carried by the fabric of space as it turns. Photons and particles that enter at different angles now find their paths twisted together, their motion inseparable from the rotation embedded in the metric. The inevitability of the singularity is written into the causal structure, but the rate at which it is approached depends on the energy and trajectory of the falling object. In the Schwarzschild case, an object starting from rest at the horizon will reach the singularity in a proper time equal to 1/2 of pi times the gravitational radius divided by the speed of light, a brief and finite interval. From the outside, this interval is never seen to complete, but for the traveller, it is as real as any measured duration. The open scientific mystery here concerns the nature of the singularity itself. In classical general relativity, the singularity is a region where curvature scalars diverge to infinity, and the known laws lose predictive power. It is not a point in space, but a moment in time for the infalling observer. Many physicists believe that quantum gravitational effects must intervene before this divergence becomes physical, replacing the singularity with a finite but extreme state. However, without a complete theory of quantum gravity, this remains uncertain. Observations cannot reach it. Only theory can suggest its nature, and even theory must admit its incompleteness. Within the horizon, signals can still be exchanged between infalling observers, and light from the outside universe still reaches inward. In fact, as the singularity draws near, the entire external universe appears to speed up. In the infaler's view, its history compressed into the remaining moments of proper time. This optical flood is not a metaphor, but a consequence of light cones tilting so far inward that every possible line of sight captures a wider swath of the outside. The brightness would increase until extreme blue shift pushes the energy beyond survivable levels for any known matter. This is the fourth quiet irony here. The deepest darkness as seen from afar is for the infaller, accompanied by an overwhelming glare of the cosmos in its last instance. Theoretical models of infall consider not just point particles but streams of matter and fields. In these models, matter falling inward can influence the interior geometry through gravitational back reaction, though the horizon itself remains unaffected by anything that happens inside. For rotating black holes, the presence of an inner horizon, a second null surface predicted by the Kerr solution, raises further questions. Classically, an infaller might pass through it, but calculations show that even tiny perturbations can grow exponentially, there creating a mass inflation instability. Whether such an inner horizon could exist in reality, or whether it would be replaced by a chaotic region of strong curvature, is still an open problem. The inward journey is silent without a medium to carry sound, and without any landmark to mark progress except the increasing curvature. The absence of friction or resistance does not mean the absence of change. Rather, it allows change to proceed without loss of speed or energy to any surrounding matter. Geodesics that began far apart outside the black hole now converge not toward a common point in space, but toward the shared moment of arrival at the singularity. This convergence can be visualized in the way light cones narrow and tilt their future directions, aligning with the path toward the center. Light stretches here not toward red as seen from the outside, but toward blue in the inhaler's own frame, the photons from the universe outside gaining energy as they fall in alongside the observer. Clocks diverge in their readings between those still outside and those within, but inside the horizon all clocks agree on the sequence leading forward, even if their rates depend on their paths. Shadows ring no longer with the photon sphere's light. The halo has been left behind, and the only boundaries now are in the geometry itself. The fall is finite in duration, but infinite in certainty. The curvature continues to rise, the tidal effects strengthen, or remain delayed depending on the mass scale, and the singularity waits ahead. Defined not by appearance, but by the breakdown of the equations that have described every step until now. The inevitability of arrival is the final soft irony of this stage, even though nothing pushes, nothing can stop, and the future is as fixed as the past in the map of space-time. The interior is still the same universe obeying the same general laws, but it is a portion from which no path leads back. Here every step inward is also a step forward in time, and the distance to the singularity is as unalterable as the passing of moments themselves. The radial fall continues not as a choice, but as the only possible extension of time. Inside the event horizon of a Schwarzschild black hole, the geodesics all end at the singularity, and in a rotating Kerr black hole the same inevitability is preserved, though the paths curve through a more complex geometry. The curvature grows slowly at first in a supermassive black hole. The tidal force is still small enough that an extended object could remain intact well past the horizon. For a stellar mass black hole, the gradient is much steeper, and any extended body is drawn out along the radial direction while being compressed laterally. This stretching and squeezing is not from any physical contact, but from the way neighbouring geodesics diverge and converge measured by the Riemann curvature tensor. It is the first soft irony here, the most violent distortion can occur in a place with no air, no sound, and no surface. As the inhaler moves deeper, space and time remain locally smooth, but the structure of space-time dictates that each tick of a clock brings them closer to the singularity. The distance is not spatial in the ordinary sense, but temporal. The singularity is a moment in the future, not a location one could detour around. A lesser-known detail here is that for massive particles starting from rest at the horizon, the proper time to reach the singularity is finite and surprisingly short. For a non-rotating black hole, it is only a few millionths of a second per solar mass, meaning that for a 10 solar mass black hole, the interval is less than 100 microseconds. This is the second soft irony. In a region so vast in gravitational influence, the end can arrive almost instantly for those who cross inside. Theories that extend beyond general relativity offer possibilities for what might replace the classical singularity. Some loop quantum gravity models suggest a bounce into another region of space-time. Other approaches, such as string theory, propose that quantum structure smears out the infinite curvature. Yet all of these remain speculative, and without observational access, the true resolution stays unknown. The open mystery is not simply what happens to matter at the singularity, but whether the notion of inside retains meaning, when the laws that define space and time themselves change. In a Kerr, black hole rotation adds further complexity. Outside the event horizon lies the ergosphere, where frame dragging forces all objects to co-rotate with the black hole's spin. Inside the horizon, frame dragging becomes absolute, and the geometry includes an inner horizon and a ring-shaped singularity in the idealized solution. Between the outer and inner horizons, the causal structure allows time-like paths to avoid the singularity briefly, but perturbations in realistic scenarios likely destroy this stability. Mass inflation near the inner horizon is predicted by perturbation analysis. Even small amounts of infalling radiation can cause the local energy density to grow, without bound collapsing the structure into a region of extreme curvature. This instability raises the possibility that the inner horizon does not exist in physical black holes, replaced instead by a turbulent zone where classical geometry fails completely. Another quiet irony emerges in how this structure is defined. The horizon, the photon sphere, and the singularity are all determined by the same equations, yet they are invisible to those passing through them in their own frames. The observer notices only the distant universe changing its shape and brightness, the light from behind being bent forward, the light from ahead becoming ever more blue-shifted. Infall toward the singularity in a Schwarzschild geometry is symmetrical from every direction, but in a Kerr geometry, the rotation twists the incoming light into spirals, and the polar and equatorial approaches can differ in tidal intensity. One lesser-known detail is that even within the horizon, the conservation laws still hold locally. Energy and momentum are conserved in each small patch of space-time, and the laws of physics as tested in laboratories still apply in their familiar form. What changes is the global picture. The set of possible trajectories is constrained by the causal structure, so that all futures lead inward. For the infaller, there is still freedom to move laterally to change velocity even to orbit in a sense, but all of these motions occur along a timeline that terminates at the singularity. From the outside perspective, signals from within are lost forever, not because they are destroyed instantly, but because the light cones tilt so far inward that no photon can ever climb back to the exterior. This contrast between local normalcy and global finality is the third soft irony here. One can live out the laws of physics as usual, even in a place where the end is unavoidable. The curvature's effect on light is not only a matter of bending paths, it also focuses beams, bringing them together or spreading them apart depending on the geodesic congruences they follow. The Raychard-Hurry equation describes how these congruences evolve, showing that under the energy conditions of classical matter, the focusing becomes infinite in finite proper time, leading directly to the singularity theorems proved by Hawking and Penrose. These theorems are purely geometric and do not depend on specific symmetries, making the approach to singularity a general feature of strong gravitational collapse. Light stretches here in its history. To the outside it fades and reddens. To the inside it sharpens and brightens with photons from the universe condensed into the last moments of time. Clocks diverge even within the horizon. Different paths to the singularity can yield different elapsed times, yet all end at the same boundary of predictability. Shadows ring no more for the photon sphere, and its luminous halo belong to the view from outside. Now the only ring is the causal closure of the horizon itself, unseen and already past. The finite time remaining can be calculated, but it cannot be slowed or reversed by any means consistent with the geometry. Even the fastest rocket, even a beam of light, cannot move outward once inside. The final approach has begun in earnest. In these last stages, before the singularity, the gradient in curvature becomes overwhelming for smaller black holes, tearing apart any composite object into its constituent particles, and then those particles into fundamental fields. For supermassive black holes, the same fate is delayed until closer to the singularity, but the outcome is unchanged. The mathematical inevitability is the last soft irony. The future is fixed not by destiny in a human sense, but by the structure of the equations themselves, which admit no solution for turning back. The interior is a region where all roads lead forward to the same point in time, where space has narrowed into a temporal end. This continuation of the fall is quiet, with no medium to carry shock or noise, no landmarks to announce distance covered. The only measure is the ticking of a clock that marches toward a moment beyond which the equations cannot speak. Here the geometry holds every future in the palm of its structure, and the singularity waits not as an object but as a limit where the map of space-time fades to blank. Within the horizon, the fall does not accelerate in the familiar way of motion through space. Rather, it proceeds at the steady rate of time itself, for the inward direction has become as unavoidable as tomorrow. The geodesics all converge toward the singularity, and there is no trajectory that can extend indefinitely. In the Schwarzschild geometry, the singularity is a point in time, but every path inside space-like in character, so that nothing can avoid meeting it. In the Kerr geometry of a rotating black hole, the interior is more intricate with layers of causal surfaces, and in the idealized solution, an inner horizon that in principle could be crossed. Yet perturbation studies show that this inner horizon is unstable, collapsing into a turbulent zone of diverging curvature. The first soft irony here is that the only route forward is also the only route available. Motion is choiceless, but still perfectly lawful. The metric remains smooth right up to the limit, and locally the laws of physics remain unchanged. The gravitational field is not a force field in the Newtonian sense, but the manifestation of the geometry itself, and in free fall one feels weightless, even while approaching infinite curvature. The second soft irony lies in this weightlessness. The greatest pull the universe can produce is felt as no pull at all. Yet the geometry's gradients cannot be ignored forever. As the singularity nears the tidal tensor increases in magnitude and nearby geodesics diverge or converge sharply. The stretching along the radial direction and compression along the transverse axis are inevitable results of the curvature described by the geodesic deviation equation. A lesser-known detail here is that these tidal distortions preserve the overall volume in the sense of the product of the axes, even as individual dimensions grow or shrink, a feature that arises from the vacuum Einstein equations in regions without matter. For a stellar mass black hole, the radial stretching near the singularity becomes extreme enough to break apart the atomic structure of any object well before arrival. For a supermassive black hole, the same distortions may be imperceptible until the remaining proper time is very small. The third soft irony is that the most massive black holes are the gentlest at their edges, yet lead to the same conclusion as the most destructive smaller ones. In a rotating black hole frame, dragging extends deep into the interior. The space-time itself rotates, and every particle, every photon is compelled to follow this twist. Even inside the horizon, the direction of rotation imprints itself on trajectories. Near the equatorial plane, light and matter spiral inward, and the path to the singularity is curved not only in space, but in the combined fabric of space and time. The rotation affects the focusing of geodesics, altering the distribution of tidal forces across different latitudes. A lesser-known feature of the Kerr interior is that the ring singularity it contains in the mathematical solution leaves open regions of space-time beyond it. However, such passages are unstable to any perturbation, and most analyses conclude they would be replaced by regions of chaotic curvature rather than traversable corridors. The open mystery is whether quantum gravity might smooth out this structure, creating something fundamentally different from the classical prediction. Inside the horizon, signals from the outside universe still arrive. The infola can see light from every angle bent inward by the curvature. As the singularity is approached, these signals arrive in a compressed sequence, with the events of the entire future history of the universe outside playing out in the remaining moments of the infala's time. This optical effect is a direct result of the narrowing light cones. Photons from increasingly distant regions are able to intersect the infala's path before the end. The fourth soft irony here is that the deepest darkness from the outside is matched inside by the brightest flood of information from beyond. In this environment, the concept of velocity relative to the outside becomes meaningless. All motion is inward in the global sense, and the speed of approach to the singularity is fixed by the structure of spacetime itself. Yet within a local frame, relative velocities between nearby objects can still be measured, and can take any value less than the speed of light. These measurements are valid but bounded by the shrinking interval of proper time before the singularity. The physical processes inside continue to obey the same local conservation laws as anywhere else. Energy momentum and angular momentum are preserved locally, and electromagnetic and nuclear forces act as they do in less extreme regions. But the space in which these interactions occur is collapsing in the temporal sense, and no arrangement of forces can change the fact that all time-like curves end at the singularity. Light stretches here in the contrast between frames. For the outside observer, it has vanished into infinite redshift. For the infala, light from outside is driven into extreme blue shift. Clocks diverge in their readings between regions, yet all clocks inside keep to a shared destiny. Shadows ring no longer, for the photon sphere is a structure of the outside geometry. The inward journey now passes through regions that cannot be matched to any spatial map in the usual sense, because inside the horizon, closer to the center, is a measure of time left not of distance that could be circumvented. In the Schwarzschild case, this remaining proper time can be computed exactly. In the Kerr case, it depends on latitude and trajectory, but in all cases it is finite. The focus of the geometry ensures that every geodesic terminates at the singularity, making it a genuine boundary of spacetime rather than just an inaccessible region. Even in this final approach, the structure is not chaotic but ordered by the Einstein field equations. The inevitable focusing of geodesics described by the Ray-Choudhury equation under the null energy condition leads to conjugate points that mark the collapse of cross-sectional areas in the congruences. These mathematical features correspond to the physical compression of dimensions, and they are the signatures of the collapse of spacetime into the singularity. The quiet, unanswered question is whether the singularity marks an actual end or a transition to a different phase of the universe. Without a theory that unites quantum mechanics and general relativity, the answer remains beyond calculation. The inward journey is finite, yet it contains the totality of the infala's remaining experience. Every step is governed by the same curvature, every moment shaped by the same equations that describe the bending of light and the slowing of time outside. The fall cannot be stopped, and in that certainty lies the last soft irony of this stage. The geometry is indifferent to the scale or nature of what it carries, treating a grain of dust and a star with the same inevitability. The singularity waits ahead, featureless in appearance yet absolute in its role as the boundary, where the known laws cease to provide answers. The map ends there not because the path is hidden, but because the structure of spacetime itself has no continuation beyond that limit in the classical theory. The interior fall is a journey through unbroken law toward the place where those laws dissolve silent and exact to the very end. The singularity's pull is not felt as force, but as the narrowing of every possible path forward until no separation remains between them. In the language of spacetime geometry, geodesics inside the horizon terminate in finite proper time, converging into the singular surface or ring depending on whether the black hole is non-rotating or rotating. The inevitability of this convergence is not negotiable. It is encoded in the Einstein field equations themselves once the energy conditions and initial collapse are assumed. The first soft irony here is that the equations are fully deterministic right up to the very place where they stop determining anything. The curvature grows without bound, as measured by invariants such as the Kretschmann scalar, which for a Schwarzschild black hole is proportional to the inverse fourth power of the radial coordinate. This divergence is not visible from the outside, yet it is a defining mathematical fact of the interior. The second soft irony lies in this invisibility. The most extreme feature in spacetime is hidden, not by distance, but by causality. Approaching the singularity tidal effect dominate the experience of any extended object. The stretching in the radial direction and compression in the perpendicular directions reach magnitudes far beyond material strength. The geodesic deviation equation describes how neighbouring world lines accelerate relative to each other, purely due to curvature without any intervening matter or force. A lesser-known detail is that the rate of this divergence is not uniform across all directions. It depends on the symmetry of the spacetime and in a Kerr black hole on the latitude of the infall. In some trajectories near the poles, the sequence of distortions can differ from those near the equator, creating a variation in the way matter is torn apart. In the rotating case frame, dragging becomes absolute. Even within the horizon, the twisting of spacetime is complete, leaving no stationary world lines relative to infinity. Light and matter spiral inexorably toward the center, and in the mathematical solution, the singularity takes the form of a ring of zero thickness but finite circumference. This ring has the peculiar property that in pure Kerr geometry regions beyond it might be accessible. Yet the slightest disturbance in realistic conditions turns this possibility unstable, creating instead a domain of chaotic curvature. The third soft irony is that the only routes predicted to lead beyond are the most fragile, erased by the smallest imperfection in the initial state. The open scientific mystery remains whether quantum gravity could preserve any remnant of these paths, or whether the classical picture of termination is final. The view of the outside universe compresses still further as the singularity approaches. In the final moments of proper time, light from ever more distant parts of the cosmos can reach the inferior, its frequency blue shifted to extremes. The sum of all future events visible from the outside can in principle be observed here, though the energy would be physically overwhelming. The fourth soft irony lies in this: the interior offers a vantage point from which all of the outside's future can be seen, yet the observer has no time to act on any of it. Infall into the singularity is not a process that can be resisted by propulsion. Inside the horizon, the structure of spacetime makes slowing down, equivalent to altering the rate at which time passes, which is impossible without altering the geometry itself. Even light is carried inward at the speed of light in the radial sense. Locally, objects can move relative to each other, orbit briefly, or follow curved paths, but these motions all take place within a narrowing funnel of possible futures that ends at the same boundary. In Schwarzschild geometry, the singularity is space-like, and the approach is the same for all trajectories. In Kerr geometry, the inner structure complicates the route, but the convergence toward divergent curvature remains. One lesser-known fact is that inside a rotating black hole, the sequence of tidal distortions can briefly reverse direction due to the frame dragging and the interplay of radial and angular curvature components. This does not prevent destruction, but alters the order of stresses encountered. Observationally, nothing from this region can be seen directly. The evidence for such interior structure comes from solving the field equations under the assumption of collapse and matching these solutions to the exterior geometry that we infer from astrophysical measurements. Gravitational wave signals from mergers tell us about the exterior space-time, but the interior remains hidden behind the horizon. its details known only through theory. Light stretches here in the contrast between frames. To the outside, any signal is frozen and redshifted away, while to the inside, light from the cosmos is compressed and intensified. Clocks diverge not just between inside and outside, but even among different trajectories inside depending on their angular momentum and starting conditions. Shadows no longer ring. The photon sphere is far behind, replaced by a deeper darkness in which no light paths remain open to the exterior. The end approaches with each tick of the infoler's clock, and the remaining proper time is both finite and unchangeable. The singularity is not a place in space, but a moment in the future that cannot be avoided once the horizon is crossed. As the end nears, the curvature grows so rapidly that no known physical process can counteract it. Quantum field theory in curved spacetime, which allows calculations of phenomena such as Hawking radiation, cannot fully describe the region where curvature reaches the Planck scale. There the known laws must give way to a theory that unifies quantum mechanics and gravity. Many proposals exist: loop quantum gravity string theory, holographic dualities, but none have been confirmed. The absence of observational input makes this the most guarded mystery of black hole physics. The final moments for any infoler are governed entirely by the geometry. Tidal distortions reach their maximum. The light from the outside universe becomes a single overwhelming glare, and then space-time, as described by the classical equations, ceases to exist in any calculable way. The fifth soft irony is that the most complete theory we have runs perfectly up to the very point where it predicts its own failure. The map ends there not because the explorers have not arrived, but because the terrain itself is undefined. Every geodesic meets this limit, every clock stops at this coordinate time, and every description in classical terms halts. The fall is over, but what if anything replaces it is beyond the current reach of science. Until such knowledge is gained, the singularity remains both the most certain and most mysterious part of the black hole's interior, a feature predicted with absolute necessity by the equations and yet hidden forever from observation. The approach to it is a journey in which the local physics is familiar, the global outcome is unavoidable, and the geometry's authority is absolute. In this, the last soft irony of the section emerges inside the most alien region of the universe. The laws of physics remain entirely at home until the very instant they have nothing left to say. Rotation changes the entire character of the space-time, and for a Kerr black hole the geometry is no longer spherically symmetric, but axially symmetric, wrapped in a permanent twist. Outside the outer horizon lies the ergosphere, a region where space-time is dragged around the axis of rotation so strongly that no object can remain stationary relative to infinity. Inside this zone, even light is compelled to co-rotate. The first soft irony here is that rotation can render rest impossible, even without physical contact, simply by carrying the coordinate grid itself. The outer boundary of the ergosphere touches the event horizon at the poles, but bulges outward at the equator. This distortion is not a deformation in matter, but a warping in the relationship between time and space directions, arising directly from the off-diagonal terms in the Kerr metric. Within the ergosphere, it is possible to extract energy from the black hole through the Penrose process, in which a particle splits into two, one falling inward with negative energy, relative to infinity, the other escaping with more energy than the original. This detail, first described in the early 1970s, has been supported in principle by numerical simulations, though its astrophysical efficiency is likely small compared to magnetic processes in jets. The second soft irony is that the most efficient engine for extracting rotational energy operates entirely in empty space, with no moving parts except the fabric of space-time. Magnetic fields in the ergosphere play a critical role in launching relativistic jets as described by the Blandford-Znajek mechanism. In this process, magnetic field lines anchored in the surrounding plasma thread the horizon and tap into the rotational energy, converting it into pointing flux that carries energy outward along the spin axis. This is a lesser-known point. The field lines themselves cannot remain static with respect to infinity inside the ergosphere, so they are wound up and accelerated, helping to collimate jets that can extend for hundreds of thousands of light years. Inside the event horizon of a rotating black hole frame, dragging becomes absolute. The coordinate singularity at the horizon gives way to an interior with two notable null surfaces, the outer and inner horizons. Between them lies a region in which the radial coordinate behaves like time, but the presence of angular momentum changes the causal structure. The third soft irony is that while rotation opens the possibility of avoiding the singularity in the pure mathematical solution, it also sows the seeds of instability that likely erase that possibility in reality. The inner horizon in Kerr geometry is known to be prone to mass inflation, where small amounts of infalling energy cause exponential growth in the effective mass parameter, producing unbounded curvature. Numerical relativity and perturbation theory suggest that this process would replace the smooth inner horizon with a violent chaotic region, though the exact nature of this region is still debated. In the ideal Kerr metric, the singularity is a ring lying in the equatorial plane with empty space in its interior. Geodesics that miss the ring can pass through into other regions of the extended solution, including hypothetical universes and closed time-like curves, yet these extensions depend on perfect symmetry and the absence of perturbations, conditions impossible in nature. The fourth soft irony is that the most elaborate pathways offered by the equations survive only in the imaginary perfection of a system that the universe never builds. Infall toward the ring singularity in the exact Kerr solution differs from the point-like encounter in Schwarzschild spacetime. The tidal forces are anisotropic, and the path taken can pass through regions of very different curvature before reaching the singularity. A lesser-known detail is that the sign of the radial tidal force can reverse for certain trajectories in Kerr spacetime, briefly compressing along the radial direction, and stretching laterally, a reversal from the pattern in non-rotating black holes. This phenomenon does not prevent destruction, but offers a reminder of the complexity introduced by spin. Observational evidence for rotation comes from multiple lines of measurement, the broad iron K-alpha lines in X-ray spectra, of accreting black holes, the frequency of quasi-periodic oscillations in X-ray light curves, and the dimensions of the shadow observed by the Event Horizon Telescope. High-spin black holes are also inferred from the immense energies of some relativistic jets, consistent with Blandford-Znajek extraction from a rapidly rotating horizon. The ergosphere's physics thus links directly to phenomena visible across millions of light years. Light stretches here in a way altered by rotation. Photons co-rotating with the black hole can orbit closer to the horizon than counter-rotating ones, and their gravitational redshift is modulated by Doppler effects from the dragging of inertial frames. Clocks diverge in their rates not only between inside and outside, but also between different latitudes and spin alignments. Shadows ring with a symmetry. In a rapidly rotating black hole, the apparent shadow is slightly flattened on one side due to these photon orbit differences, a subtle signature of the spin. For an infaller, the ergosphere is crossed without sensation, but the consequences are profound. Once inside, even light emitted directly outward cannot remain stationary. It is swept into rotation. In the Penrose process, the negative energy states are not negative in the local frame, but only with respect to infinity, a concept defined by the global spacetime geometry. The extraction of energy through such states is bounded by the irreducible mass of the black hole, which sets a limit on how much spin can be removed. In theory, a Kerr black hole can be spun down to a non-rotating state, reducing the ergosphere until it vanishes. But in astrophysical context, accretion can also spin a black hole up toward the theoretical maximum. There is an open mystery in how close real black holes get to this limit. The spin evolution depends on the interplay between accretion jet launching and gravitational wave emission in mergers. High spins have been observed, but whether nature produces nearly extremal Kerr black holes is still uncertain. The fifth soft irony emerges here: the fastest spinners may lose their advantage in stability, as near-extremal rotation amplifies instabilities at the inner horizon and magnifies tidal shear in certain trajectories. As the inward journey continues in a rotating black hole, the coordinate landscape is twisted and compressed in ways absent from the Schwarzschild case. Yet the endpoint is still a singularity where the classical equations predict the breakdown of all known structure. The ring form of the singularity in Kerr spacetime is an artifact of the model's symmetries, but its divergent curvature is a robust feature. The approach to it is guided not only by the pull of gravity but by the twist of space and time themselves, carrying everything into the deep rotational core. In this motion, the last soft irony of the section rests. Rotation gives the black hole an active role in shaping what falls into it, yet the outcome for the infailure is the same as in the stillness of the non-rotating case: a finite future, a final moment, and then no geometry left to describe what follows. Deeper inside a rotating black hole, the theoretical maps of the Kerr solution begin to show structures that have no counterpart in the non-rotating case. The inner horizon, or Cauchy horizon, marks a surface where determinism in the classical sense fails beyond it. The future is no longer fixed solely by past conditions, and the predictability that underlies general relativity breaks down. In the perfect mathematics of the Kerr metric, this horizon could be crossed smoothly, opening a route to other regions of spacetime in the maximal analytic extension. The first soft irony here is that this doorway is both a product of the most exact solution we have, and one that reality almost certainly will not allow. Perturbation analyses suggest that the inner horizon is violently unstable to even the smallest in falling radiation or matter. This instability, called mass inflation, arises because radiation trapped between the outer and inner horizons is infinitely blue-shifted as it falls inward, causing the effective mass parameter to diverge. A lesser-known detail is that the blue shift at the Cauchy horizon is not uniform across angles. It is strongest along certain trajectories aligned with the rotation, leading to highly anisotropic distortions in the geometry before the horizons collapse. The second soft irony is that the very rotation that creates this inner horizon also ensures that it is the most unstable place in the black hole's interior. In the physical universe, numerical simulations and perturbative studies indicate that the inner horizon would be replaced by a chaotic region of extreme curvature, perhaps a null singularity or a turbulent transition layer. This outcome would erase the smooth passage envisioned in the ideal Kerr geometry and remove the possibility of travelling to other universes or avoiding the central singularity. Yet even with this likely replacement, the mathematics of the inner horizon remains valuable for understanding the causal structure of rotating spacetimes and for framing the open problem of how general relativity and quantum mechanics reconcile in strong gravity. Inside this region, the twisting of spacetime by rotation is absolute. Inertial frames are so thoroughly dragged that all trajectories spiral inward along the spin axis. Light co-rotating with the black hole can skim closer to the singularity before capture than counter-rotating light, but no photon can escape once inside the outer horizon. A lesser-known point is that the distribution of tidal forces in the rotating interior is more complex than in the Schwarzschild case. Depending on latitude, the radial stretching can briefly switch to compression, while the transverse directions expand a reversal from the pattern outside. This does not prevent destruction, but alters the sequence in which an extended body is torn apart. The third soft irony emerges here: rotation can change the path to disintegration without altering the certainty of it. For an infaller, the approach to the inner horizon would be accompanied by the most intense blue shift of light from the outer regions, compressing vast spans of the external universe's future into moments of proper time. This influx would be dominated by radiation trapped and circling between the horizons, its energy growing without bound in the classical picture. Physically, such an energy flood would likely destroy any matter long before it reached the mathematical horizon. The fourth soft irony is that the view would contain more information than could ever be delivered in a burst too intense to survive. If the ideal Kerr extension could exist without instability crossing the inner horizon, would lead into a region where the radial coordinate regains its role, as space and time flows in multiple possible directions. The metric would allow navigation toward the ring singularity or avoidance of it, even opening paths that loop through other asymptotically flat regions. In this picture, the ring singularity itself would be a structure with a central hole passing through it. Along certain trajectories would miss the divergent curvature entirely. This is the feature that creates closed time-like curves in the extended Kerr geometry paths that return to their own past. Yet the slightest deviation from the perfect symmetry introduces tidal stresses and gravitational shocks that make such travel impossible in practice. This is why most relativists regard the exotic passages of the maximal extension as mathematical curiosities rather than physical realities. Observationally, no direct evidence can confirm or refute these inner structures. They are hidden behind the outer horizon and beyond the reach of light. Their study depends entirely on the field equations supplemented by numerical work to explore what happens when the ideal symmetries are broken. Light stretches here in more ways than one. Outward-directed photons are still trapped. Inward-directed photons are accelerated to unimaginable energies, and the very definition of stretch and compress becomes direction-dependent in the rotating geometry. Clocks diverge profoundly, and infaller's clock runs evenly in its own frame, yet from the perspective of any hypothetical observer still outside it, ticks toward an end that will never be seen. Shadows no longer ring. The photon orbits that once defined them are far behind, replaced by light paths that swirl through the rotating interior before ending in capture. The open mysteries of this region are not small. They include whether the mass inflation instability inevitably destroys the inner horizon, what the resulting singularity would look like, and whether quantum gravity might allow some remnant of the extended Kerr structure to survive. Loop quantum gravity, holographic dualities, and other approaches have proposed mechanisms to resolve or replace the singularity, but without observational input these remain untested. A lesser-known observation is that gravitational waveforms from black hole mergers might in principle contain subtle post-merger echoes from perturbations reflecting within the interior, but such signals would be faint and their detection uncertain. The fifth soft irony rests in the fact that our most detailed mathematical maps of the rotating interior may describe a landscape that nature erases instantly upon creation, and yet those maps have shaped decades of work on the frontier between relativity and quantum theory, providing a stage on which the limits of both are tested. As the inward journey proceeds in this picture, the curvature grows in complexity as well as magnitude, and the singularity, whether ring-shaped or chaotic, remains the unavoidable terminus. Rotation changes the route, it alters the tidal patterns, it creates horizons within horizons, and it even permits on paper the avoidance of the singularity. But in every realistic scenario, the future for an infaller ends in finite proper time, with the same absence of any path forward. The last soft irony here is that rotation, the very property that gives black holes some of their most spectacular observable features, from jets to asymmetric shadows, ultimately cannot change the fact that inside all timelines meet the same end. At the threshold between the exterior universe and the unobservable interior, the event horizon acts not as a surface in the ordinary sense, but as a boundary in the map of causal relationships. Its geometry carries with it an unexpected thermodynamic identity, a temperature and an entropy defined by the laws of black hole mechanics. The first soft irony here is that a region from which nothing escapes can be described as having a temperature that would in principle allow it to radiate. In the semi-classical framework developed by Stephen Hawking quantum field theory, in curved space-time shows that virtual particle pairs near the horizon can become real with one particle falling inward and the other escaping to infinity. The escaping particle carries positive energy away, while its partner inside reduces the mass of the black hole. This effect produces Hawking radiation, a thermal spectrum with a temperature inversely proportional to the black hole's mass. For stellar mass and supermassive black holes, the temperature is far below the cosmic microwave background, making the radiation undetectable with current instruments. A lesser-known detail is that for a black hole of one solar mass, the Hawking temperature is about 60 nanokelvins colder than any laboratory environment, except those specifically engineered for ultra-cold physics. The second soft irony is that the hottest conditions known in the universe's formation have their theoretical opposite in the coldest object imaginable, and both extremes arise from the same fundamental laws. The entropy of a black hole derived by Jacob Bekenstein is proportional to the area of its event horizon in Planck units, not its volume. This proportionality suggests a deep link between information and geometry, since entropy measures the number of possible microscopic configurations consistent with the macroscopic state. The third soft irony emerges here. The most compact object has the largest entropy of any object of the same size, yet that entropy scales with its surface, not its interior. The four laws of black hole mechanics mirror the four laws of thermodynamics with surface gravity, taking the role of temperature and horizon area replacing entropy. In any classical process, the area of the event horizon cannot decrease a result known as the area theorem. Quantum mechanically Hawking radiation provides a way for the area to shrink, but the generalized second law, which includes both black hole entropy and ordinary entropy outside, is still preserved. The open scientific mystery is the exact nature of the microscopic states that account for this entropy. In certain string theory, models counting the configurations of branes and strings has reproduced the Bekenstein-Hawking entropy formula for specific types of black holes. But whether this result extends to all black holes is unknown. Holographic principles suggest that all the information contained in a volume can be represented on its boundary, a concept inspired in part by black hole entropy scaling. Light stretches here in the sense that Hawking radiation photons emerge at wavelengths, corresponding to the black hole's temperature, which for astrophysical black holes are exceedingly long. Clocks diverge in how they measure the timescales of evaporation. For a distant observer, a black hole radiates and shrinks over immense spans, while for the black hole's own frame, the concept of evaporation is not locally observable. Shadows still ring in the sense that the photon sphere shapes the observed outline, but Hawking radiation emerges isotropically and carries no image of the interior. A lesser-known fact about Hawking evaporation is its extreme slowness for large masses. A black hole of solar mass would take about 1067 years to evaporate completely, a duration many orders of magnitude longer than the current age of the universe. For a supermassive black hole of 1 billion solar masses, the evaporation time is on the order of 10^99 years. These numbers are so vast that the radiation is negligible compared to any astrophysical process we can measure now. Yet for hypothetical small black holes with masses comparable to mountains, the Hawking temperature could reach billions of kelvins, producing intense gamma-ray emission and evaporating in seconds. Searchers for such primordial black holes have looked for these final bursts without success so far. The connection between black hole thermodynamics and quantum theory deepens with the information paradox. If Hawking radiation is purely thermal, it carries no record of the details of what fell, in suggesting that information is lost when the black hole evaporates. This loss would conflict with unitarity, a fundamental principle of quantum mechanics that says the evolution of a closed system preserves information. Proposals to resolve this paradox include the idea that information is encoded in subtle correlations within the radiation, that it is stored on the event horizon in a holographic form, or that it is recovered at the end of evaporation through some as yet unknown process. None of these has been proven, and the paradox remains one of the most important open questions in theoretical physics. The fourth soft irony here is that an object that hides everything about its interior might over inconceivable spans reveal all of it through the faintest and coldest of glows. Observations that could test these ideas directly are far beyond our present capabilities, but indirect approaches such as studying the analog Hawking radiation in laboratory systems that mimic horizons have offered insights. Experiments with flowing fluids, optical fibers and Bose-Einstein condensates have simulated horizon-like conditions and produced radiation consistent with the Hawking prediction. While these analog systems cannot capture all the complexities of quantum gravity, they strengthen the case that the effect is real and tied to general principles of field theory in curved spacetime. Another lesser-known aspect of black hole thermodynamics is the concept of black hole chemistry, where the cosmological constant is treated as a pressure term and the black hole mass as an enthalpy. In this framework, black holes can undergo phase transitions analogous to those of ordinary substances such as liquid-gas transitions in charged or rotating black holes. While primarily of theoretical interest, these analogies further suggest that the laws governing horizons may be part of a broader and deeper thermodynamic structure. As the perspective returns to the infalling frame, none of these thermodynamic properties is apparent locally. Crossing the horizon feels the same whether or not the black hole is radiating. Hawking radiation is a feature of the global spacetime structure and the behavior of quantum fields across it. The last soft irony of this section is that the thermodynamic personality of a black hole is visible only from the outside to observers who never cross in. For those who do, the geometry continues without hint of temperature or entropy, the local physics indifferent to the global bookkeeping of information and heat. From afar, the event horizon is a surface with temperature, entropy, and a faint radiation. From within, it is nothing more than another step along the geodesic toward the interior, silent about the processes that distant observers calculate in its name. The two views are both correct, each complete in its own domain, yet they describe realities that can never be joined in a single frame. The processes that shape a black hole's growth and transformation are often hidden in the glare and turbulence of its immediate surroundings. When two black holes merge, their horizons do not collide like solid surfaces, but rather blend seamlessly, forming a single larger horizon, in accordance with the area theorem. The first soft irony here is that while the merger is an event of immense violence in energy release, the horizons themselves unite in perfect smoothness, without shock or fragmentation. In the moments before coalescence, the space-time around each black hole is distorted by the gravity of the other, and the orbital motion produces ripples in space-time gravitational waves. These waves carry away energy and angular momentum, allowing the orbit to shrink until the horizons meet. The detection of gravitational waves from binary black hole mergers by LIGO and Virgo has confirmed this process with signals matching the predictions of general relativity to remarkable precision. A lesser-known detail is that the gravitational wave signal contains 3 distinct phases: the in-spiral, where the frequency and amplitude increase as the orbit decays, the merger, where the 2 horizons join, and the ring-down, where the distorted final horizon emits gravitational waves at characteristic frequencies until it settles into a stable Kerr state. The second soft irony lies in the fact that the most unyielding objects in the universe announce their unification by sending out vibrations in the very fabric of space and time. The ring-down phase offers a direct probe of the properties of the final black hole. Its oscillations, known as quasi-normal modes, are determined entirely by the mass and spin of the black hole, independent of the details of the merger. Measuring these modes allows tests of the Noether theorem, which states that black holes are completely described by mass, spin and charge. So far, observations are consistent with this theorem, though future detectors with greater sensitivity may be able to detect subtle deviations that could hint at new physics. The third soft irony is that the identity of the final black hole, stripped to 2 numbers, erases all trace of the complexities that created it. In some mergers, the recoil from asymmetric gravitational wave emission can give the remnant black hole a velocity of hundreds or even thousands of kilometers per second. A lesser-known point is that if this recoil exceeds the escape velocity of its host galaxy, the black hole can be ejected into intergalactic space, wandering without a surrounding disk or companion stars. While such events are rare, they show that even objects defined by capture and confinement can themselves be cast adrift. On larger scales, black holes also grow through accretion, the gradual accumulation of matter from surrounding gas and stars. Matter falling toward a black hole forms an accretion disk where viscous forces heat it to extreme temperatures, producing X-rays and sometimes powerful jets. The efficiency of this process is high. Up to 42% of the rest mass energy of matter can be converted to radiation for a maximally rotating Kerr black hole, compared to about 0.7% for nuclear fusion in stars. The fourth soft irony is that the most efficient known engine for turning matter into energy works not by consuming it in fire, but by guiding it through a calm curve of spacetime toward disappearance. Observations of active galactic nuclei show that jets can emerge from regions very close to the event horizon, aligned with the spin axis of the black hole. These jets are powered by a combination of magnetic fields, frame dragging, and rotational energy extraction. A lesser-known detail is that the collimation of these jets can remain stable for millions of years, implying a persistent alignment between the spin of the black hole and the structure of the surrounding galaxy. Changes in jet direction seen in some systems may indicate that the black hole's spin axis itself is precessing due to gravitational interactions with another massive object. Mergers between supermassive black holes expected to occur during galaxy collisions will produce gravitational waves in much lower frequencies than current detectors can measure. The planned Laser Interferometer Space Antenna LISA will target this range, potentially detecting such events out to the earliest epochs of galaxy formation. These signals will provide insight into how supermassive black holes assembled over cosmic time. Light stretches here both in literal wavelength shifts from the relativistic motion of accreting matter and in the metaphorical sense of carrying information from processes hidden behind the horizon. Clocks diverge between the steady ticking in the far universe and the rapid rhythms near the innermost stable circular orbit. Shadows still ring with a photon sphere's light, but the structures producing the jets and X-rays lie within a few gravitational radii of the horizon, where space and time themselves are distorted. The open mysteries of black hole mergers and growth include the spin distribution of black holes across different masses, the role of mergers versus accretion in building supermassive black holes, and whether certain spin states are favored by the dynamics of cosmic structure formation. Gravitational wave astronomy is still in its early years, and each new detection adds to the statistical picture. Future observations may reveal populations of black holes with unexpected properties, or evidence of exotic compact objects that mimic black holes in some respects but differ in their horizons or interiors. A lesser-known consideration is that the ring-down phase might carry faint imprints of the black hole's near-horizon quantum structure, if such structure exists. These hypothetical echoes would arrive after the main ring-down signal caused by partial reflections just outside the horizon. Detecting such signals would require sensitivity beyond current capabilities, but they remain a target for theoretical modelling. The fifth soft irony of this section is that the most powerful confirmations of general relativity come from events that in their final moments destroy all direct evidence of what happened inside. We learn of the merger's perfection from the way the waves match the predictions of a theory that offers no window past the horizon. From the perspective of an infaller, the joining of two black holes is simply a continuous extension of the geodesic into a new interior. There is no jolt, no seam, only the unbroken curvature carrying them forward. From the perspective of the distant universe, it is a brief flash in gravitational radiation, followed by the quiet persistence of a single larger shadow. The two descriptions are both correct, and together they tell us that spacetime's most extreme events can be both violent and seamless, both informative and concealing, both the product of immense complexity and the origin of utter simplicity. The event horizon marks a boundary not only for light, but for every form of electromagnetic observation. Even the Event Horizon Telescope linking radio observatories across the globe to create an Earth-sized interferometer can only resolve the silhouette cast by the photon sphere. The first soft irony here is that the most direct images we have of black holes are pictures not of the holes themselves, but of the light they fail to capture. In the case of M87, the shadow appears as a dark circle encircled by a glowing ring. This ring is made of photons that have skimmed near the photon sphere before escaping toward us, many of them completing partial orbits that amplify their apparent brightness. The diameter of the shadow is larger than the horizon by a factor of roughly 2.6, a geometric effect independent of the black hole's size. A lesser-known detail is that while the EHT observations were presented in warm gold and orange colours, these hues are false, chosen to aid interpretation. The actual emission is in the millimeter radio band invisible to human eyes. The second soft irony is that we colorize what we cannot see not to change the truth, but to make it perceptible to our limited senses. Observing the surroundings of a black hole requires capturing light that has been bent redshifted and time-delayed by the curved spacetime. In systems with bright accretion flows, this light comes from electrons spiraling in magnetic fields producing synchrotron radiation. The distribution of this radiation depends on the temperature and density of the plasma, the strength of the magnetic field, and the motion of the gas. General relativistic magnetohydrodynamic simulations are used to model these processes, producing synthetic images that can be compared to actual observations. The third soft irony is that our most realistic pictures of black holes are as much the product of computation as of observation, the telescope and the equation working together to reveal a single scene. In addition to direct imaging, black holes can be studied through their influence on background light. Gravitational microlensing, in which the gravity of a compact object bends and magnifies the light of a more distant star, can reveal the presence of black holes, too small or isolated to be seen otherwise. A lesser-known fact is that the duration and shape of a microlensing event's light curve can constrain the lens's mass, allowing astronomers to identify candidates for stellar mass black holes without accretion disks, Such detections complement the gravitational wave observations probing a different part of the population. High-energy observations from X-ray telescopes also trace black hole environments. In X-ray binaries where a black hole accretes matter from a companion star, the inner edge of the accretion disk approaches the innermost stable circular orbit. The iron K-alpha line produced when X-rays illuminate the disk is broadened and skewed by a combination of Doppler shifts and gravitational redshift, creating a characteristic profile that can be modeled to estimate spin. Light stretches here both in wavelength and in path tracing arcs that may loop near the horizon before emerging. Clocks diverge in the observed timing of variable sources as processes in the inner disk appear to slow in gravitational time dilation relative to distant frames. Shadows still ring, but the brightness of the ring fluctuates as magnetic turbulence churns in the plasma, creating hotspots that can orbit at relativistic speeds. The open mysteries in observational black hole science include the exact structure of the magnetic fields near the horizon, the role of magnetic reconnection in powering flares, and the relationship between accretion state and jet launching. Observations of Sagittarius A. The supermassive black hole at our own galaxy's centre are particularly challenging because its variability is faster than M87 was, blurring the image during long observations. A lesser-known challenge is that interstellar scattering caused by irregularities in the plasma between Earth and the galactic centre distorts the radio waves, requiring careful calibration to reconstruct the true image. In spite of these difficulties, the EHT has produced images of both M8070 and Sagittarius A that match the predictions of general relativity within current uncertainties. Future expansions of the array, including space-based antennas, could improve resolution and allow imaging of black holes with smaller angular sizes, such as those in more distant galaxies. There is also the possibility of producing time-resolved movies of the inner accretion flow, revealing the dynamics of material as it spirals inward. The fourth soft irony of this section is that the most extreme regions in the universe unreachable in person may become more familiar through sequences of images made from light that has travelled across millions of years. Beyond direct imaging, black holes are studied through their transient outbursts. Tidal disruption events occur when a star passes too close to a supermassive black hole and is torn apart by tidal forces. The debris forms a temporary accretion disk, producing a flare that can outshine the host galaxy for months. Observing these events provides information about the black hole's mass and spin, as well as the physics of accretion onset. A lesser-known outcome is that in some disruptions, relativistic jets are launched for the first time in the black hole's history, producing brief but powerful radio and X-ray emission. The fifth soft irony is that while black holes can feed steadily for millions of years, some of their most revealing behavior comes in rare catastrophic meals. The observational frontier continues to push toward detecting intermediate mass black holes, which would bridge the gap between stellar mass and supermassive black holes. These have been elusive with only tentative evidence from gravitational waves and star cluster dynamics. Confirming their existence would help explain how the first supermassive black holes formed so quickly after the Big Bang. Observational tests of general relativity in the strong field regime also depend on these studies, as deviations from the Kerr metric might be detectable in precise measurements of black hole shadows, gravitational wave ringdowns, or orbital precession of nearby stars. Yet so far, every test has reinforced the theory's predictions, suggesting that if new physics exist here, it hides with extraordinary subtlety. For the infaler, none of this observational grandeur is apparent. The horizon is crossed without spectacle. The shadow and ring exist only for those who remain outside. The inside journey is indifferent to the colours we assign the simulations we run or the data we gather, From afar, the black hole is a canvas where light is bent, delayed, and raced. From within it is simply the geometry of time leading forward. The last soft irony of this section is that everything we can know of a black hole's appearance is shaped by light that never crossed the horizon, meaning that our most complete images are still of the outside, no matter how deeply we study. Beyond what is visible to telescopes, black holes are investigated through their role as engines of gravitational waves, ripples in spacetime that carry information not in light, but in the direct deformation of distance. These waves, predicted by Einstein's field equations, are generated when massive bodies accelerate asymmetrically, and their production is especially strong in the final moments before two black holes merge. The first soft irony here is that the cleanest proof of black holes' existence arrives not from light, which they forbid, but from waves they cannot prevent. The detections made by the Laser Interferometer, Gravitational Wave Observatory and its counterparts have confirmed dozens of binary black hole mergers, each signal a brief chirp that sweeps upward in frequency and amplitude. By matching these signals to numerical relativity simulations, astronomers can extract the masses and spins of the colliding black holes and test general relativity in the strong field regime. A lesser-known detail is that the signal from a stellar mass binary black hole can pass through Earth in less than a second, yet it can be detected from billions of light-years away because it changes the length of the detector arms by a fraction of the width of a proton. The second soft irony is that the most massive and compact events in the universe announce themselves with distortions so small they are invisible to any sense but measurement itself. Gravitational wave signals carry no direct image, but their phase and amplitude evolution encode the dynamics of the system. In the inspiral phase, the orbit shrinks, gradually emitting waves of increasing frequency. The merger itself is a nonlinear regime where spacetime curvature is at its peak, producing the largest amplitude. The ringdown is the final relaxation of the merged horizon into a Kerr state radiating at quasi-normal mode frequencies determined solely by mass and spin. A lesser-known point is that the relative amplitudes of different modes can reveal whether the final black hole's geometry matches the Kerr prediction, offering a test of the no-hair theorem. The third soft irony here is that the most complete portrait of a black hole's identity can be drawn from a signal that contains no light at all. Gravitational wave astronomy also probes questions of black hole populations. The masses of merging black holes detected so far include examples heavier than previously expected from stellar evolution models, suggesting formation channels involving repeated mergers or low metallicity stars. Spin measurements hint at both aligned and misaligned configurations, pointing to multiple formation scenarios such as isolated binary evolution and dynamical assembly in dense stellar environments. A lesser-known finding is the discovery of a binary black hole with a component in the pair instability mass gap, a range where certain models predict no black holes should form from single-star collapse. Such detections challenge existing theories and drive revisions to models of stellar death. Light stretches here in a metaphorical sense. The information carried by gravitational waves complements what photons can reveal, extending our vision into the realm of mass and motion directly. Clocks diverge in that gravitational wave detectors measure time not by regular ticks, but by the oscillations of spacetime itself as a signal passes. Shadows still ring in the electromagnetic domain, but here the ring is the oscillation of the merged horizon traced in pure geometry. The open mysteries in gravitational wave science include whether we will detect intermediate mass black holes, whether the ringdown phase will ever show clear deviations from Kerr predictions, and whether subtle post-merger echoes could indicate exotic horizon structures. Some theoretical models propose that quantum gravitational effects might partially reflect waves just outside the horizon, producing a sequence of delayed signals. While current detections have not confirmed such echoes, future instruments with greater sensitivity could search for them. A lesser-known aspect of gravitational waves is their potential to test the propagation of gravity itself. By comparing the arrival times of gravitational waves and light from the same event, such as a neutron star merger, we can constrain the speed of gravity to an extraordinary degree. While no confirmed electromagnetic counterpart has been observed for a binary black hole merger, any such detection would provide further tests of fundamental physics. The fourth soft irony of this section is that the quietest messengers, waves that pass through matter without scattering, may one day tell us whether gravity behaves differently at extreme scales. On much larger scales, planned detectors such as the space-based laser interferometer space antenna will target gravitational waves with periods of minutes to hours, ideal for detecting mergers of supermassive black holes. These events expected from galaxy mergers will offer a chance to test general relativity in regimes of curvature and mass far beyond those accessible to ground-based detectors. Pulsar timing arrays, which measure the regular pulses of millisecond pulsars across the sky, are already detecting hints of a gravitational wave background, possibly from the combined effect of many supermassive black hole binaries. A lesser-known implication is that this background may carry information about the history of galaxy formation and the growth of black holes over cosmic time. For an infaller, none of these distant observations intrude on the experience. The gravitational waves they generate in their final approach are not felt locally. They are distortions in the geometry that leave no tactile signal, only the measured stretching and squeezing of space far away. The fifth soft irony is that while black holes can send their presence across billions of light years through pure space-time motion, they cannot announce it to the one who is part of that motion. From the viewpoint of gravitational wave astronomy, black holes are both subjects and instruments. They create the signals we measure, and they serve as laboratories for the very laws that predict them. Every new detection refines our understanding of their masses, spins and rates of formation, and every match between theory and observation strengthens the framework of general relativity. Yet the same framework tells us that what happens beyond the horizon, the place where the waves themselves are born, will remain unseen. This is the last soft irony of the section. The very waves that confirm black holes exist are generated in regions whose details they can never carry to us. They are perfect messengers for the story of the outside, but they leave the inside exactly as silent as before. The question of what happens to information that crosses the event horizon remains one of the most persistent and careful puzzles in modern physics. In classical general relativity, any matter or radiation that falls into a black hole adds to its mass angular momentum and charge, while every other detail, the fine structure of the particles, the arrangement of their quantum states, is erased from the exterior description. The first soft irony here is that in this picture, the universe's most complete destroyer of information is described by equations that themselves conserve information everywhere else. Quantum mechanics, in contrast, insist that the evolution of a closed system is unitary. The total information about its quantum state is never lost, only transformed. Hawking's calculation of black hole radiation complicates this further, because the thermal nature of the radiation seems to carry no record of what fell in. When the black hole evaporates completely, nothing appears to remain that could encode the original information. This apparent contradiction is the information paradox. A lesser-known detail is that Hawking's original argument assumed a fixed background spacetime, not accounting for back reaction of the radiation on the geometry, a simplification that may omit crucial correlations. The second soft irony is that the result that most challenge the foundations of physics may rest on the very approximation that made it calculable. Many proposed resolutions exist. One is that the information is preserved in subtle quantum correlations within the Hawking radiation, so that while the radiation appears thermal at first glance, careful measurement of its long-range correlations would reveal the imprint of the initial state. Another is the holographic principle, which posits that all information in a volume can be represented on its boundary, implying that the event horizon could store the necessary degrees of freedom. A lesser-known implication of this view is that the entropy of the horizon proportional to its area may literally count the number of independent quantum states available to encode information. The third soft irony here is that the most complete description of the interior might be painted on its surface. Other ideas challenge the smoothness of the horizon itself. The firewall proposal suggests that if information escapes in the Hawking radiation, the horizon cannot remain a benign place for an infoller. Instead, high-energy quanta would be present at the horizon, breaking the equivalence principle locally. This would replace the quiet crossing predicted by general relativity with a sudden destruction of the infaller at the horizon. The majority view among relativists is that such a violation of the equivalence principle is too extreme, and alternative models such as fuzzballs in string theory attempt to avoid firewalls while still preserving unitarity. A lesser-known variation is the soft hair hypothesis, in which low-energy excitations of the gravitational and electromagnetic fields on the horizon encode the information of what has fallen in. This view preserves a smooth horizon for the infaller, while allowing the exterior to carry a detailed record over time. Light stretches here not only in the literal sense of gravitational redshift, but in the metaphorical sense of information being distributed over large scales in space and time. Clocks diverge in the way they mark the black hole's life to the distant observer. Evaporation takes eons, while the interior clock of an infaller reaches its end in finite moments. Shadows still ring, but their structure tells us nothing of whether information is stored, destroyed, or transformed. The open mystery is whether the information paradox will ultimately be resolved by a complete theory of quantum gravity, perhaps revealing that space-time itself emerges from more fundamental quantum relationships. Holographic dualities such as the ADS-CFT correspondence offer an example of how a gravitational theory in a higher dimensional space can be equivalent to a non-gravitational theory on its boundary with manifest unitarity. Yet these dualities are best understood in highly symmetric spacetimes, not in the exact conditions of astrophysical black holes. The fourth soft irony is that the most promising tools for resolving the paradox are derived from universes that are not our own. Attempts to detect signs of new physics at the horizon through gravitational wave, echoes near horizon modifications to black hole shadows or quantum imprints in Hawking radiation are ongoing, but so far none have found definitive evidence. Laboratory analogues such as sonic black holes in Bose-Einstein condensates have simulated horizon-like conditions and observed radiation consistent with the Hawking process, but these do not yet address the question of information preservation directly. A lesser-known experimental direction is to use quantum computing to simulate simplified black hole models, testing whether unitary evolution can be recovered in systems that mimic the essential features of evaporation. From the perspective of the infaller, none of these debates change the experience the horizon is crossed without drama. In general relativity, the interior geometry carries the trajectory forward and the singularity still lies ahead. The fifth soft irony is that the deepest disagreement between quantum theory and relativity is invisible to anyone actually inside the black hole, unfolding entirely in the mathematical comparison of viewpoints that no single observer can hold. For now, the paradox remains unresolved, a boundary where two great frameworks of physics stand intact in their own domains, yet incompatible where they overlap. The search for a resolution is as much about the nature of spacetime and quantum reality as it is about black holes themselves. It may be that the horizon is not a perfect divider, that spacetime is not fundamental, or that quantum mechanics itself must be generalized. Until these questions are answered, the event horizon will remain more than just a place in spacetime. It will be a meeting point for the limits of human understanding. From afar, the black hole is a clean, simple solution to the Einstein equations. From within, it is a finite journey to a singular end. And in the mathematics that bridges the two, it is an open question whose answer may redefine what it means for information to exist. Beyond the final clock tick inside a black hole, classical general relativity has no further instructions. The singularity is a place where curvature invariants diverge, where geodesics cannot be extended, and where the very coordinates of spacetime lose meaning. The first soft irony here is that the theory that has mapped everything from planetary orbits to the evolution of the cosmos ends by predicting its own inability to continue. For the infaller, the singularity is not a point to be approached in space, but a moment in time, one that cannot be avoided and cannot be extended beyond. In a Schwarzschild black hole, this moment lies a finite proper time ahead for every trajectory inside the horizon. In a Kerr black hole, the ring singularity of the mathematical solution offers more structure in theory, but in reality the instabilities and perturbations would likely destroy any of the delicate pathways that avoid direct encounter with divergent curvature. A lesser-known detail is that the singularity shape is a property of the spacetime's causal structure, not of any material surface. It is defined entirely by how the metric behaves, not by anything that can be touched or seen. The second soft irony is that something with no material form can nevertheless be the most absolute end in the universe. What lies beyond is a question for quantum gravity, a theory not yet complete. It is widely expected that quantum effect will soften or replace the classical singularity, perhaps turning the divergence into a finite but extreme region, or connecting it to other regions of spacetime. Loop quantum gravity models suggest a bounce in which collapse transitions into expansion in some form. String theory approaches with their extra dimensions and extended objects offer other mechanisms for smoothing curvature. Yet these ideas remain speculative, constrained more by internal consistency than by direct evidence. The third soft irony is that the most carefully calculated possibilities for the end of spacetime are also the ones least likely to be confirmed by observation. There is an open scientific mystery in whether spacetime is continuous at the smaller scales, or whether it is discrete, built from more fundamental elements. If it is discrete, then the singularity might be avoided because curvature could never truly become infinite. If it is continuous, then some other principle must intervene to halt the divergence. Holographic principles suggest that everything within the black hole is encoded at the horizon, so that the singularity might be less a place than a bookkeeping artifact in a dual description. A lesser-known implication of this view is that the interior might not exist as an independent region in the fundamental theory, even though it is a valid solution in the effective classical geometry. Light stretches here into impossibility. There is no light beyond the singularity to carry any record outward. Clocks diverge for the last time. The infaller's own time reaches its final moment, while the outside universe's clocks continue indefinitely. Shadows do not ring here. They belong to the world outside, which is already sealed away. In the classical picture, the journey ends with the destruction of any structure, the crushing of all separation between points. In the quantum picture, the end may be transformed into a passage, but without a completed theory, this remains an open line in the ledger of physics. For the cosmos at large, black holes will persist for unimaginably long durations, their horizons growing with each merger or accretion event, shrinking only on timescales of Hawking evaporation. Supermassive black holes in galaxy centers will survive the deaths of their stars, the cooling of interstellar gas, and the dispersal of their galaxies into the expanding universe. In the far future, they will be among the last luminous objects as they slowly radiate away their mass. A lesser-known detail is that in the so-called black hole era of the universe, after 1040 years, most remaining mass will be locked in black holes, and the slow drip of Hawking radiation will be the primary source of energy in the cosmos. The fourth soft irony is that in a universe once filled with bright stars, the last light will come from objects defined by their darkness. After the evaporation of the final black holes on timescales that stretch beyond 1099 years, for the largest, the universe will enter a phase of extreme simplicity, with only low-energy particles and vast distances between them. Whether information is preserved through this process or lost forever remains unknown. The information paradox unresolved would still apply even in this ultimate quiet. It is possible that the decay of black holes encodes their histories in a form too diffuse for any observer to reconstruct. It is also possible that the records are perfect, but inaccessible, preserved in correlations that no measurement could ever gather in full. The fifth soft irony is that even if the universe keeps every secret ever dropped into a black hole, it may still be functionally the same as if the secrets were gone. In the present epoch, our view of black holes is framed by observation and theory by the shadows in EHT images, the chirps of gravitational waves, the light curves of tidal disruptions, and the precise agreement of strong field tests with general relativity. For the infoler, none of this exists. There is only the geometry and the path it dictates. For the theorist, the black hole is both a complete solution and an incomplete story. From outside, it is a long-lived object with a measurable mass spin and perhaps charge. From inside, it is a finite span of proper time to an unresolvable end. Between these views lies the gap where quantum gravity must someday speak. Until then, the singularity is the purest expression of where our knowledge stops, a point in the mathematics where the map simply ends. That ending is not a failure, but a marker telling us where new principles must be found. The last soft irony is that the most absolute feature of black holes, the place where space and time themselves cease, may one day be erased not by falling into it, but by understanding it. The motion slows not in speed, but in the way thought drifts when there is nowhere left to reach. Outside, the universe continues its light forever sealed beyond return. Inside, the curvature no longer seems to change. It simply is a stillness too complete for measure. Time has narrowed to its final moments, but the sense of passage is gentle without urgency. No boundaries remain to cross. No horizons stand ahead. The geometry folds into itself, and even the idea of direction dissolves. Light no longer travels. Distances no longer mean. What was once path becomes only the memory of movement, then the memory of memory fading without trace. All clocks are quiet now. Shadows are gone. The last rings of light have long been left behind. There is no horizon here, only an unbroken absence that holds nothing and asks nothing. If the outside could see in, there would be nothing to see. If the inside could see out, there would be nothing to look for. The fabric rests. Curvature rests. The infoler rests. The equations have no further instructions. It is the same stillness that fills the space between stars, the same stillness that lingers in the deep ocean, the same stillness that lives in the pause between heartbeats. Here it has no interruption, no end. The journey into the black hole does not close with the sound, but with the removal of all need for sound. It is not an ending as much as the final absence of beginnings. What remains is not something that can be kept, only the weightless quiet that was always here beneath the motions and the lights and the time. Rest lies in every direction now. The universe continues elsewhere. In here there is only this.